test it.
Okay, should be good.
All right, well, I hate to be the last speaker, but that's how I guess it worked out today. So who is excited not to learn about nutrients? Anyone else? Oh, we got 3 people. All right, go home. All right. we can tell you this stuff later, or you can read the slides. They're pretty self-explanatory. So today my task is that you're gonna see a lot of me tomorrow morning. I think I have 2 more talks. So today we will start conversation on nutrients, and so this part 1 will touch on nitrogen, phosphorus, which you all know are the 2 major nutrients that we deal in terms of water quality issues in Maryland. So tomorrow morning we'll talk about potassium and sulfur. That's the first talk. And then in second talk we will talk about soil sampling, and then we'll talk briefly about Can you all hear me okay in the back? Okay, awesome. So I'm sure by now you have figured out that nutrients are plant food, right? So we need them to grow crops, and for various reasons. Usually when there's a nutrient deficiency, that's when we start talking about nutrients, or we have too many nutrients in a water body that cause algal pollution, and algae is also a plant. Other than that, we don't really hear about that. So I'm sure you have seen pictures of nitrogen deficiency, which is more sort of yellow. Phosphorus is more sort of purple in the leaves. Fortunately, in our state, we rarely see phosphorus deficiency because we have a lot more phosphorus, which you all know. But we do have fields where it can occasionally show up. And nitrogen deficiency is sort of more common in most of the systems, including our state. So here, what you're going to learn here is how plants get nutrients. Like, so if we need food, we can go to supermarket because we are mobile, right? We can go to fast food, another restaurant. Unfortunately, plants can't. So they need to have food somewhere in their proximity to access that food. So there are 3 ways. One is that as the root is growing, it bumps into, food. And I mean, a good example here will be a buffet if you are here. Like that will be an example that you bumped into. The second is moss flow, which means there's enough water in the soil, and as the water is moving, depending upon where there's a less or more water, the nutrients, as they're soluble, will move and hit the root, and the root will be able to take that out. The third part is what's called diffusion. So I'm going to turn this off so it doesn't bug us. So diffusion is, so in soil, you always have one area where there's a higher concentration and there's a lower concentration. And think about when you add fertilizer, right? So fertilizer is applied at some place, but roots may not be there. So in that situation, the nutrient from the higher concentration will move to to the part of the soil where there's a less concentration, just to establish equilibrium. Like if you spill water, it's going to go in some direction, right? Because there's a lot more in one place compared with another. So when we look at the 3 nutrients here, nitrogen and phosphorus, and you can sort of see that nitrogen pretty much moves with water because nitrogen is mobile, which is nitrate. That's why nitrate is very quickly leached or lost from the soil. If you compare that with phosphorus, it's always with the diffusion. And there are several reasons. First, the concentration of phosphorus is much lower than the nitrogen. And secondly, phosphorus is also very strongly retained by soil, which means soil doesn't let it move. So the only way it can go from one place to another in terms of root acquisition will be moving from higher concentration to lower concentration. And in case of potassium, it's very similar to phosphorus, except there is some potassium that's soluble that can also move to the roots. So knowing these things, you can sort of think about that if you're adding nitrogen fertilizer, we don't need to really apply where the roots are going to grow, right? But in case of phosphorus and potassium, if we are not applying where the roots are, I'm going to show you some slides here, that could be a challenge. And that's where the idea of bending the fertilizer comes into play. I'm sure you've heard about that phosphorus should be band of light. So band is a small narrow strip where you are growing roots. So if you plant your crop right within that band, there's a high chance that the plants will be able to take that. Right? So everything clear? All right. So the next thing to know is, how much do you need? So a good example will be, we drink different amounts of water and different foods, right? So similarly, for plants, they have differential needs. They need different nutrients. In some ways, a balanced diet, so to speak. But if we are comparing nitrogen with phosphorus, you can kind of see that plants need 4 times more nitrogen, because here it's 1,000 and it's 250. And if you are comparing with phosphorus, plants need much more nitrogen than phosphorus. And then we have a bunch of other micronutrients that we're not going to touch on today. So moving on to the first part of the presentation, nitrogen. So these are the 5 things we're going to talk about. We'll talk about nitrogen cycle, how nitrogen is fixed. Then we'll talk about some transformations of nitrogen from one form to another, as they're important for plants acquisition. Then we'll briefly touch on the role of carbon. How does that affect the nitrogen behavior in soils? And then finally, what could we do to reduce nitrogen losses, and what are the main pathways through which nitrogen is lost from the soils? Okay, so nitrogen is actually a very interesting and a fascinating nutrient to study, and part of the reason is it exists in many forms. So in the soil, it can also be fixed. It's always in the solution, like nitrate that moves. Nitrogen also has a gas form, like 78% of our atmosphere contains nitrogen gas. With nitrogen, the nitrogen cycle is dictated by soil microorganisms. So as they're doing different things in the soil, in the process they also change nitrogen forms and nitrogen behavior in the soil that ultimately influence how much nitrogen could potentially be available to the plants. So here is, we've got 78% nitrogen, 20% oxygen. So this is good environment for humans or the sort of the life to sustain. That's why we are on Earth, and this is also the reason that we can't be on Mars, because there is a very little oxygen and it's more carbon dioxide dominated system. Like so, and I'm sure you all been hearing about what's going on. We're going to go on Mars and try to do things. So the atmosphere is not favorable in that case. One of the good advantages with high CO2, if you can figure out water and microbes, you can actually grow a lot of plants, because plants need CO2 as part of the photosynthesis process. So the nitrogen discovery is actually a fascinating story, and you will think that we have known nitrogen for a long time, but we actually haven't. Back in 18th century, there was a chemist. He sort of discovered nitrogen in 1772, and then fast forward to another 70 years. Then we sort of realized that, hey, it's a nutrient. Plants can use it. Fast forward to another 50 years. We learned that there are some plants that can fix nitrogen. And then go into early 19th century, when we sort of figured out how to make fertilizers. So there is a process called Haber and Bosch process. These were 2 German chemists who discovered how to make fertilizers, like nitrogen fertilizer. So this is also called industrial fixation. And if you look at this sort of faded line, this line is actually the number of people on Earth. So if you look back in 1900 to 1950, we were less than 1 billion, right? And you fast forward to another 100 years, we are right now, this is an old slide, but we are somewhere here now, 9 billion pretty soon. And so there are sort of similarities that the invention of nitrogen fertilization process has allowed us to multiply quickly, because we can grow more food, right? So back in the day, one of the major bottleneck was the availability of food. So many of the folks back then, they will migrate to different places, usually river valleys or other places wherever food was available. So the invention of fertilizers allowed us to be stationary live at one place and get food because we can grow in a small piece of land to support a large population. So it's a pretty fascinating story. If you're more interested and you're bored of watching whatever is on Netflix, Google this thing. It's actually a pretty nice story. There's also a podcast on it. It's pretty cool. And again, like so legumes, we talked about this, fertilizers. So this is a complicated slide. I want you to memorize this. No, not. Okay, so there are a couple of things going on. All the green things are the losses in this slide, right? So all the sort of blue, whatever that shade you see, these are all nitrogen forms. So nitrogen exists in different forms in the soil in different places. And somewhere in the middle is what we call plant uptake. So I'm going to run through a lot of text, but you don't have to memorize because you have the slides. So among all different nitrogen forms, plants can only use what's called inorganic forms, right? So those inorganic forms are nitrate and ammonia. That's it. This probably will be a question on your test at some point. So what happens, the plants take up like nutrients, and then we harvest corn, the stalk somewhat stays there, goes back into the soil, that's when it starts decomposing, right? So in plants, that nitrogen is present as what's called organic form. So when the plants decompose, the organic nitrogen goes back, and this nitrogen is then converted back into what's called ammonia, right? That's another nitrogen form, and there's a process that we will talk about that. And then that ammonium from the plants, is converted now to another process called nitrate, and it's called nitrification. So we'll talk about that. And then that ammonia then is converted to another form, which is a loss, which is your volatilization here. So if you follow this diagram along with this, you can pretty much figure out where the arrow is going, right? So, and this also talks about here, you know, you have ammonium, and this is your nitrification and other processes. So this could be useful as you're sort of preparing for your test. And again, nitrate is also lost through another process. So we're gonna spend actually several slides on this, so hang around there. So if we look at all these losses that happen to nitrogen, so when you apply, let's say 100 pounds of nitrogen to a field, you're only going to recover or utilize the plants about 1/4 to 3/4, right? Because the rest of the nitrogen is lost depending upon the field's circumstances, other situations, other factors that influence nitrogen loss. And this gets more complicated and messy because each field is different. So the challenge is, how do we keep more nitrogen in the soil so plants can use it? That's a bigger term sort of question, and we haven't yet figured out how to do that. So we're going to touch about some of the mechanisms that you saw in the previous slide. So when we talk about how nitrogen is fixed, so this is industrial process, and we talked about Haber-Bosch process. This is fertilizer manufacturing. So pretty much, so in our atmosphere, we got 78% nitrogen gas, right? So if somehow we can take that, which will be pretty easy, you know, you can use sort of an advanced way to suck that air into a system, and then you have high pressure. Think about a gas tank, high pressure, and then when you start heating that up at high temperature, that nitrogen, which is two molecules, they break down, and they combine with hydrogen to form what's called ammonia, right? So once you do that, then you got ammonia as a sort of a base to make any other fertilizer that you could make. So this is the industrial process. This is how we make fertilizers. So if you look at, so that's one way, right? There's also natural fixation. So if you remember lightning, so lightning is very strong when lightning happens. So we have 78% nitrogen gas, which is two molecules of nitrogen, and you see 3 lines. This is called 3 bonds. So it's the strongest bond, one of the strongest bonds in organic chemistry. So when lightning hits whatever, it can actually break down that bond. When that happens, the nitrogen is mixed with the water that's falling and falls back. So we actually get quite a bit of deposition. We used to get a lot more, but now we get a little bit less because we have better catalytic converters in vehicles and other places. The other process that's more relevant to agriculture is what's called the biological process. I'm sure you all know legumes have nodules, for example, and in the nodules you have a bacteria called rhizobium. So this bacteria is, think about how powerful this bacteria is, that it can actually break down that nitrogen bond from the air and it can fix nitrogen. And that's whenever you're growing legume, either as your cover crop mixture or as a direct like soybeans, alfalfa, our recommendations are not to apply nitrogen because these crops can fix nitrogen. They can meet their nitrogen needs by drawing nitrogen from the environment, which is pretty cool. And this process is called symbiotic because you have sort of a good relationship with the bacteria and the plant. And there's another relation. So this means that both are benefiting, right? So bacteria is benefiting by growing, at the same time plant is benefiting because plant is getting nitrogen. So there's another process. This happens. It's called free living bacteria and blue-green algae. So a good example will be a algal bloom in a water body that doesn't have enough nitrogen, right? So in most cases we do, but we also have some of the lakes where we don't have enough nitrogen, and in those cases we see that there is an algae. So we have now learned over the last few years that there are some species of bacteria who can actually fix nitrogen just as legumes do. And this is not good. It means that we can reduce all the nitrogen going to that water body. And if you have certain species of algae and bacteria, they can still take nitrogen and meet their needs, which means they can grow and there will be more yucky stuff in the lake. So here are sort of some examples. If you look at these numbers, are astonishing. So if you're growing alfalfa, you can actually fix a lot of nitrogen. And if you remember, our recommendations for corn is about 200 pounds of nitrogen for 200 bushels of nitrogen. This is a lot of amount. Which if you look at soybean, that's why we have no recommendations for nitrogen because they don't need nitrogen. And some other species, just as a reference, that how much nitrogen they can fix. So these are large amounts. Okay, so moving on to the transformation, and this is how one nitrogen form is converted to another. Like, so there are two processes. So you have a big organic nitrogen pool in the soil, and the process is called mineralization. So the way to memorize will be mineral is like inorganic, right? So it means now you're going from organic to inorganic pool. And when you look into the inorganic nitrogen pool, so let's see, you have these three species, pretty much ammonia and nitrate. And then there's the intermediate product, which is nitrite. Now we'll talk about that. So if you look at total, how much is this inorganic pool? It's tiny in the soil. But if you look at these arrows, which means after this pool is utilized, there's a large reservoir in the soil that can release more nitrogen back into the soil. So this is the sort of, think of this as a pantry, and this is your dining table. Like, so there's enough nitrogen available in systems. So the opposite of that process is called immobilization. So immobile, not, in other words, taking away nitrogen that's present in the soil in these inorganic species, because these are the forms that plants gonna use, right? So if this goes back into this pool, this is not good. And it happens, and we'll talk about that why. So again, just a refresher again, mineralization. It's a process where organic nitrogen is converted to inorganic form. In this case, we are talking about ammonia. This is all done by the microbes in the soil. The opposite of this process is immobilization, right? So in this case, we are converting inorganic, not only ammonia, but also nitrate, both forms back into the organic nitrogen. This is also all organisms. There are a lot of them in the soil, and in certain situations, they can actually take the nitrogen, and as a result, plants can't access it, which is not good. Okay, another process, this is nitrification. So the best way to memorize is nitrate, and then you got nitrate in the beginning, right? So if you see this nitrate, you can just guess it's gonna be a nitrate process. So this is again, biological means done by microbes, but this process begins with ammonia. You need to have ammonium to begin this transformation. That's one. Second, you need aerobic conditions, right? And you can guess that in ammonium, there's a hydrogen, which anytime you see hydrogen in an element, it means lack of oxygen pretty much in that system. And anytime you see oxygen, it means aerobic conditions, means there's enough air present, right? So you need enough of ammonium, and then you need enough air, and then if you also need the right pH. If the pH is low, it can kill the microorganisms and the process won't go forward. And so it's also all bacteria doing things for us. So the way nitrification happens is, again, we talked about ammonium, right? So there's a little bit of air, and this ammonium will start getting converted to an intermediate form, which is called nitrite. And then there's a more air present, and now you have nitrate. So this is the product we are interested in from the plant side. In most of the soil systems, this is really tiny, because once you have air that begin that process, most likely the conversion will be complete. The only places where this accumulates more is wetlands, where the water levels fluctuates. Like, so imagine that there was some air and this conversion happened, but now there's not enough air in the system, and then nitrite accumulate, which is not good, because nitrite can be toxic in different situations, including us. If we drink water that has more nitrate, that can cause toxicity. Okay, so I think by now you all have figured out that soil nitrogen cycle is driven by microbes, right? So, and there are other factors that influence pH, we just talked about, is critical. Temperature, that's another factor. More hot it is, more action will happen in the soil. And also we just talked about moisture. If you don't have enough sort of air or oxygen in the system, many of the transformations connected with nitrate won't happen. Okay, so this is just a slide on a sort of primer on temperature. Let's see what happened. So just a reference point, this is 32, water freezes. When you have over winter, the point of this slide is in winter time, there is not a whole lot of happening to nitrogen transformation, right? So because it's cold, right? So nothing is being transformed at that point. But once we get to 70 degrees, like this time of the year, now this is a good temperature for nitrification. Once we get a little bit more hot into June and July, that will be good for mineralization. And we know that we never get to temperature here, and which is good, because that can kill most of the microbes. And there's also analogy. This is like, you think about, nature pretty sophisticated in a way, that the optimum temperature for most of the crops is somewhere 70 to 80, which corresponds with some of the transformations that happen in the soil. So temperature, so this is a complicated, but I'm going to try sort of simplifying it. So I'm sure you all learned that in soil you got solids, then you got air, and then you got water, right? So solid is about 50%, rest of that is air and water combination, like that's called pore space. So if you now take the full pore space, exclude the solid, then consider 100 pore space means all the pore space in the soil. So let's say in this example that it's very dry to begin with. Like, so in that case, you're gonna be somewhere here. It's very dry, there's not enough moisture in the system. So what's gonna happen in this situation? So in this process, there's enough air, because there's a lot of air. This is water filled. So 100 will be saturation, like if you're standing water. Here, it's almost bone dry. So this is the sweet spot for nitrogen conversion, because there's a lot of oxygen available, right? And there's a little bit of moisture, because it limits when you get hit to zero. When you get past half of that pore space filled, there's not enough air. So the nitrification or the conversion of, in this case, ammonia to nitrate stops, because there's not enough oxygen for that conversion. And now think of this scenario if the field is flooded. At that point, there will be complete saturation, right? So, or somewhat. In that case, that nitrate that we just converted is going to be converted back into a process called denitrification. So denitrification is a transformation of nitrate to nitrogen gas that goes back in the atmosphere. And this happens naturally. In some ways, it's good. If we don't have this process happening, our water bodies will be loaded with nitrogen. The downside is in the soil situation, if a field is flooded, which usually happen in spring, that you applied fertilizer, now it rained, and there's a water standing, and that nitrate now is getting lost, which is an economic loss, not a good situation. So it depends where we are looking at. Okay, so carbon is the one that drives microbial cycle, right? So carbon is food for microorganisms who drive nitrogen cycle. So it's pretty important. One of the sort of indicator of carbon is how much carbon is there relative to nitrogen. So what we call carbon to nitrogen ratio. So you're gonna see this in a bunch of slides and other places. So generally a high CN or carbon nitrogen material means there's a lot of carbon, but very little nitrogen. So because bacteria, the microorganisms need both, right? So as they start decomposing, they also need more nitrogen to grow. So if there's not enough nitrogen in the system, they will end up taking nitrogen, whatever is there, and take it back into what's called immobilization, which means the process won't be complete for conversion of nitrate. So we like to see less carbon nitrogen material added into the soils so that you can have more nitrogen mineralized so that plants can use it, right? That's the goal of this process. And here is the data reminder of the pool mineralization, which is your inorganic and back into immobilization. So with the lower CN ratio, it will go in this direction. If you have more high CN, it will go in the opposite direction, which is not good. Some examples here of some of the materials that are used in the sort of soil setting. So if you're using sawdust, you can see very, very high CN ratio. And with this, most of the nitrogen that's present in the soil is not going to be available. It's going to be immobilized. And there are some other sort of species here. We don't really apply sewage sludge directly, but biosolids would be close enough. So again, so the point here is that when you are you need to keep an eye on the carbon to nitrogen ratio so that there is enough nitrogen available for the plants. So here is cover crops is a good example. So if you're growing a lot of cover crops that don't have legume in the mixture, I'm sure you all are hearing multi-species cover crops that have a sort of legume component. And the idea is if you grow a multi-species with legume in it, you can actually reduce the CN ratio of that material, which means that more nitrogen could be mineralized. Like so, here are some thoughts here, but keep an eye on that CN ratio. Okay, so this is the bigger challenge. How do we reduce nitrogen losses, right? So fertilizers, they were never cheap, but this year I'm sure they are not cheap. It costs a lot of money to buy fertilizer. But if the fertilizer is applied so that the farmer can get profitable yield, but if that's not going to be there, it's a loss. It's an economic loss to the producer, and it's an environmental loss to the society who has to deal with consequences of those. So the couple of ways that nitrogen is lost is what's called volatilization. We'll talk about that. This is a gas loss that happens when it's hot and dry, and then you have erosion runoff. It's usually slopes, heavy rain, think of Western Maryland. Denitrification, we just talked about more water in the soil. One of the things that happen in most settings is leaching. This is nitrogen that goes down the soil profile. All right, so we're going to spend some time talking about each of these components. So leaching loss is lost as a nitrate because, again, remember mass flow in the beginning. Wherever water goes, nitrate goes. Cause pollution, and it's actually very high under the modern row crops because we apply a lot of nitrogen. Again, it's an economic loss that has environmental consequences. So if someone ever asks you that nitrogen has two forms, nitrate and ammonium, right? Why does nitrate leaches, but ammonium doesn't leach? Here is a slide. Here is a little bit chemistry. Nitrate is negatively charged. Organic matter, everything is negatively charged. They repel each other. Nitrate is out of the system. Ammonium is positively charged, and it's strongly attracted and it stays in the soil. So ammonium is fixed in the soil. Nitrate is not. So excessive nitrogen, inefficient nitrogen management, right? So a lot of nitrogen is applied one-time application. Think of pre-plant. and we want our producers to not apply pre-plant, because if you add all the nitrogen in the beginning when nothing is in the ground and you got rain, and you know what's going to happen to that. It's going to be gone. And this also connected with improper timing. Nothing is on the ground. And over application of manure can also be a huge source. And this is the key here, that you can add all the things. If it doesn't rain, it's not going anywhere. But we can't control the rain, so we have to manage how and when we apply nitrogen sources. Here's an example from 2018. Who was in Maryland in 2018? Everyone? You all remember the spring rain, the 1 week time period, anywhere from 5 to 8 inches. This is just 1 week, a lot of rain. And it happened at a time when pre-plant applications already had happened, right? So these are some pictures. So this is a sort of visual on your leaching, like a lot of water, and it's gonna leach down. Here is the example from Western Maryland. You have runoff. Here is another example when the water is standing, that nitrate is now being converted to nitrogen gas. So this is the part of the challenge. How do we avoid situations such as this? Okay, ammonia volatilization. We do have some concerns with gas loss, but remember, we are in the sort of east of Mississippi temperate climate zone, right? So these losses are much, much higher in the western part of the country, especially during spring, summer, because the soils are dry, there's not enough moisture, but we do have concerns about this. So this pretty much means loss of ammonia, and it begins with ammonium to begin with. And it affects anything that's added on the surface, because the sun will hit and the ammonium will be converted to ammonia gas. And what you need is warm, dry weather. So there are a couple thoughts on here. Again, this is also economic loss, right? It's gone. But more importantly, if you think about it, if nitrogen is lost from a manure, right, it's going to affect the nitrogen to phosphorus ratio, right? So if that affects nitrogen phosphorus ratio, it means if someone added a 200-pound basis nitrogen, but you had ammonia loss, that's not going to be exactly 200 pounds of nitrogen at that point. Like, so it's part of that is gone. Whatever that will be 20, 50 pounds. Now you're only left with 150. So you might wonder that, hey, I added enough manure, but I didn't get the yield because part of that was lost. And that also means that we also have ammonia loss from stockpiled manure, for example, who was tested at one point and sitting in a field for a while, and now it's being applied. And this is going to concentrate more phosphorus in the manure, because there will be less nitrogen available per unit of phosphorus. That's another concern. So these are some of the favorable conditions. Like so again, it's hard to predict, but ideally, if you're spreading manure and you can sort of time it perfectly, that you're gonna get 0.3 inches, 0.4 inches of rain, it's good, because this will seep manure back into the soil and you will have less loss. Temperature, so this is critical, that if the temperature is high, there will be more ammonia loss. Wind, if there's a lot of wind, that's going to replace the airflow, which means more ammonia loss. Humidity, dry weather is not good, cause more ammonia loss, and some other factors. So generally, when it's dry, there's a more evaporation, water evaporation, more ammonia loss. All right, so what could you do with it, right? So again, knowing situations like the previous we talked about will be helpful. Most of the ammonia loss happens on the first day of application. This is the most critical time. So if you can avoid sunny, low humidity, breezy conditions when manure is spread, you can minimize. And again, if you can incorporate that somehow with the soil, which means now you're mixing with the soil, and some of the ammonium will be fixed and not lost. So that's also good. Another thought, if you're spreading manure, don't do it at noon. It's hot, right? So if you can do it in the evening, then that might actually reduce the losses, since most of the ammonia loss happens in the first day. Here's denitrification. We went over, it's exactly opposite of the other process. So we start with the nitrate, it's now more water, so the bacteria needs oxygen to survive. They attack the nitrate molecule, and you can see 3, 2, now you're left with 1. Little bit more longer, that oxygen is also gone, so you end up with nitrogen gas, goes back into the atmosphere. That is already the 78% again, saturation of the soil is the factor. And I'm sure you all have seen, this is a wet spot in the field, right? So for other non-ag people, they might be wondering what the hell happened there. But it's pretty obvious in this situation that rainfall occurred, right? And this is a low spot in the field. And that in that situation, the nitrogen that was once added as nitrate ammonia is gone as denitrification, so you don't have enough nitrogen available. So again, that's challenging. How do you manage that? In some of the fields on the shore, this is a good spot to actually put tile drains, right? But not every field is suitable, and we have some fields where tile drainage is practiced. So again, these are broad ideas, but it's easier said than actually trying to improve the soil drainage. One thing could be done is delaying nitrogen application, right? So in this situation, if you do notice that spot where it's gone, it will be a good idea to go back and just add some nitrogen in that spot so that you can recoup the nitrogen loss that has happened. So again, what could you do? Soil pH is critical, reduce losses, apply fertilizers when they need it. And this is more sort of a complicated question because we apply most of the nitrogen in the beginning of the spring when nothing is on the ground, which is a bad idea. That's why we suggest split application, that you can add a little bit and then do some split applications in June when plants are actually growing and they need it. But then that's another issue, getting the equipment, and if you have more rain, so it gets more messy and complicated. Again, if you have an option, you can incorporate some of the stuff, that's always good. A lot of sort of emphasis on 4 hours, which is, to me, is common sense. If you practice that, that can help that. All right, so some of the challenges with nitrogen, we don't have a direct nitrogen test, right? That's one of the challenges that we are dealing with. There's a lot of variability, not only within a field, but also across fields. It's a complex cycle. A lot of microorganism action is going on. Cover crop, manure, how much nitrogen is coming and where that's going. Again, I think there's a lot more to improve. So again, split applications are a really good start. So as you start working on a farmer's nutrient management plan, encourage them to do split application. That's the low-hanging fruit, so easy to do. We also have pre-site nitrate tests. Utilize that, it's cheap. I talked to the county advisor, they will run the test for you. And again, there are other thoughts on how could you account for nitrogen that's coming from legumes and cover crops and manure so that you can reduce the net amount of fertilizer that a farmer has to purchase. All right. Emily, how much time I have left?
Let's see.
20 minutes?
Kendra, what time is it supposed to
We're scheduled to end at 3:45, but if
Okay. It might take 5 more, but I'm going to skip a few things. Okay, so we're done with the nitrogen. I'm sure you have had a lot. I wish I can give you 10 minutes break, but we can't. So we're gonna cruise along. We're gonna talk about phosphorus. The good thing is phosphorus cycle is kind of boring. There's not a whole lot going on, right? So it's good and bad depending on how you look at it. Again, there's no gas farm, so you add it, it stays there. That's it. Again, but it has some other issues because of that, and it's because of phosphorus chemistry. So again, like a lot of stories here. There's a sort of story on how this was discovered. So we're gonna briefly talk about the phosphorus behavior in soils, plants, fertilizer, manures, and then finally we get to the big issue that we deal with in our state. So this is self-explanatory. You can read it. Pretty cool story. Again, very nice podcast is available on how phosphorus was discovered by a chemist who was trying to, back in the day, everyone wanted gold, right? These days, everyone wants crypto till stock market almost crashed, a couple of weeks ago. Back in the day, if you wanted to get rich, if you have a gold, you are gold. So everyone was looking for a way to make things gold. So this chemist, this is Germany, I'm not sure what was going on back then, probably a lot of beer and a lot of bathroom breaks. So this guy was like, okay, urine looks like gold, right? So he thought there might be something in it. So he probably fed a lot of beer to a bunch of people, collected all the urine and started boiling. And when he boiled, he saw there was this white substance left in that. And he thought, he got something. Because there were two things: you want to get rich, and there was a lot of magic happening back in the day, right? So if you can do philosopher's stone, which means you can control other people and other things. So he thought he is onto something, but in the process, he actually discovered phosphorus. So there are two ways you can get, this is red phosphorus. We haven't seen phosphorus, we haven't smelled phosphorus, but you have heard about phosphorus if you're in Maryland. So this is how we mine from the soil. This is red phosphorus that's mined from the soils. We have mines in the country, North Carolina, Florida. Another white phosphorus that we often see is fireworks. So you see all the white and different colors, that's actually phosphorus loaded material that's getting burned because it just is really such a good way to see phosphorus in action. So in a natural setting, go back before agriculture, 10,000 years ago, most of the phosphorus, and still in the soil, it comes from the rocks. So as rocks start weathering, rocks have minerals. One of the minerals we have is apatite. When that breaks down, that adds phosphorus. But in our modern soils, the managed soils, most of the phosphorus is present in organic farms because we've been growing crops for a long time in those soils. So those crops, when they go back, straw goes back, start decomposing, more phosphorus is added, and it's all organic. And again, there's a little bit more present in other fractions here. So these are you don't have to memorize anything, but I just want to highlight that there are a lot of forms of phosphorus in the soil. Most of them don't do anything, they just stay in the soil. This is the form that we are most interested in, which is called orthophosphate, which is available to the plants and other issues that comes with it. Okay, so this is phosphorus cycle. So if you look on the top there are four sources in most of the fields. You've got fertilizers, residue, agricultural waste, manure, biosolids, combinations. And in the middle of that is what's called soil solution pool. This is where plants take up nutrients. This is where the phosphorus is lost from the soils. And then we have a little bit of leaching that happens in the soil. It's also erosion runoff that gets into surface waters and groundwaters. All right, and if you look on the left, this is where most of the phosphorus resides because it's fixed in sort of different ways in the soils. So just like nitrogen, there are different processes. These are phosphorus processes. So there's something called sorption, means sorbed, gone from the soil solution, and desorption means now back in the soil solution. And you have another form called precipitation, means it's taken out, like in mineral precipitation, and dissolution means that mineral is now dissolved. And then you have another word, it's called dissolution again, because the mineral is finally broken down and it added more phosphorus back into the soil solution. So pretty simple. I hope you don't have to memorize this. There's also a lot of organic P here. So that's like biomass, organic matter, and other stuff that's going on. So talking about a transformation fixation, so we just briefly touched upon it, is there are many processes in the soil too. This is fixed. This is absorption or sorption. If you see that they're same, this is an old name, and the new name is sorption. There's another word is precipitation. Again, in acid soils, so what's that process? So in most of our soils are acidic soils, which means neutral or less than neutral pH. We have a lot of aluminum and iron in those soils, right? So when you add phosphorus, because of its chemistry, it can very strongly bind with aluminum and iron. And that's why phosphorus stays in the soil for a long period. So if you keep adding phosphorus in the same soil where you have iron and aluminum, the next thing that happens is the next one, which is mineral. So I'm already on the next slide. We don't have to worry about this in our area because we don't have what's called calcareous soils. These are soils with a high calcium, like the soils you will see in the western part of the country. We don't have those because we have a lot more rain than that part of the country, like Arizona, for example. So now you started the process with aluminum, but there's more phosphorus added, and we found secondary minerals. So it keep on combining, and this is where this process is called precipitation. I mean, it's gone now. Again, there's another in sort of high pH soils. We don't have to worry about that. So pH has a great control on phosphorus. So this will be something when you're working with a producer. Always first look at the pH because that's going to tell you a story. It's equivalent to testing temperature of any organism to see what's actually happening, and pretty easy to do. So again, this is because phosphorus pool is tiny, but it's variable, and most of the phosphorus is available between 5.5 to 6.87 pH, right? So by checking pH, you can be sure that pH is not the one who's messing up phosphorus availability. And in most of the soils, you're going to end up here. We also lime the fields to get into the right range, and that's one of the reasons that if you're in the right pH zone, not only for phosphorus, but also for a lot of micronutrients and another, that's one of the requirements to actually have the right pH. And also remember, if you have a pH less than 5.5, it's also going to mess up nitrogen cycle, right? So you want to stay in this range. 6 is good. So phosphorus loss, again, doesn't really happen. It happens on the western side of the state. If you have a slope, heavy rain, the sediments are gone, and so is phosphorus. There's a little bit of leaching loss, but it can be significant because the amount of phosphorus, if you remember the first slide, plants need 17 times more nitrogen than phosphorus, right? Which means that you can lose 17 times less phosphorus than nitrogen and still have issues with water quality. So that's part of the story. It leaches just a little bit, and that's even enough to cause water quality issues. Plant uptake takes tiny amounts. Again, this is another way to sort of look at phosphorus cycle. This is the soil solution pool where plants will take up. Then you have the intermediate pool, when you apply fertilizer, for example, and then you have this non-labile is all minerals, which is not available, but they can become available over a longer period of time if we stop applying phosphorus on those fields. So again, some factors, sort of explanatory, that because phosphorus, if you remember, plants get it through diffusion, right? High concentration to lower concentration. So the roots are very critical and how they're spread out in the field, and some other processes that happen in the roots, because as roots are decaying, they add other sort of acids back that can help with phosphorus availability. Again, some other phosphorus uptake process that we briefly touched on. So this is it's self-explanatory. If there are low phosphorus soils, the plant's going to grow more roots. That's the first thing, so that they can get more phosphorus from the system. So plants have a mechanism. If you think about in most of the forest settings, unmanaged forest, the trees are growing, right? They're getting nutrients from somewhere. And in some situations, the roots can be very deep, because if you don't find what you're looking for, they're going to go hunt in the field. And the opposite side of the story is when we get into high field situations, there's enough available already. So plants don't need to expend that energy to grow more roots. It's a pretty basic biological phenomenon that all the plants and other species, they get lazy. And we have obesity problems in the country. Why? Because we can Uber food to us, right? We don't have to go anywhere else to do that. It's the same with plants. It's the same story. They don't want to expend energy. There's enough. And in this case, they actually start putting the phosphorus out into the sort of surrounding environment, because too much phosphorus can be toxic to plants in itself. So something to keep in mind, because some people have the perception that when you have enough high phosphorus, you still need to add more phosphorus. No, you don't need to add phosphorus. There's enough in the system already. Again, I just wanted to kind of see that the mother of all the phosphorus fertilizer is rock phosphate. Just like nitrogen gas. It all begins with the soil. So we can mine it, go through different processes, and make different fertilizer. This is what the fertilizer industry does. And once you have that, you can now add some sort of nitrogen that we made from ammonia, and you can make MAP or diammonium phosphate and some other different combinations as are needed. This is another sort of example that phosphorus doesn't move in the soil. So once you add it, it stays there. One way to sort of visualize would be that, let's say you apply, this is where the granule of phosphorus was applied, right? So you go 1 inch far where that was applied, and you look at the availability, tiny, because it doesn't move, right? The second thing is, even if you look at the same spot where you added, and then you look from 1 day to 28 days, that phosphorus is gone because it's fixed by the soil components that exist. So this sort of reinforces the idea that banding phosphorus fertilizer is the best way to get more out of that application. And this is like another, again, example that when you apply granule, what happens to that? And we know it's mostly diffusion. But this is something, this is the sort of take-home message, that apply phosphorus fertilizer close to the roots by bending so the roots can access it pretty quickly. Manures are pretty good source of phosphorus. Most of the phosphorus is 100% available because of the animal do a really good job in digesting it. Especially with the dairy manure, it's all available. In poultry litter, we have a little bit of organic phosphorus that's just not available right away, but it can become available over a period of time. That's why we assume that all the phosphorus that's added with manures and organic waste is pretty available. Okay, so I think we are almost going to be done in less than 3 minutes, I think. So we talk about legacy phosphorus. Like, this is another buzzword that people are using, and you're going to come across from people like Emily talking about legacy P. So what does that mean is that we add a lot of phosphorus in the soil, right? So everyone has a different definition of what is legacy. So in other words, soils that have high phosphorus means there is a history of application of phosphorus in that field. And application of that historical application resulted in phosphorus levels which are now in the high FIP category. So there's a good story that if you look at before World War II, there were small farms, so there were probably few animals. They produce manure. That manure go back in the field. That's where the grain was grown, and less use of fertilizers back in the time. So there was sort of a circular system that the nutrients from the manure are recycled on the field, and the grain is consumed and then goes back into the field. So everything was in sync. We didn't have these hot spots of more nutrients in one field or different areas. And then you fast forward, this is also part of the nitrogen story. You have to look at these stories together, because now we started making fertilizers, not only nitrogen but phosphorus. So in this example, this is phosphate rock from Florida mines, being taken into Midwest. That's where the grain is grown. That's where corn and beans are. And now they have a lot more grain than the people can utilize it. Like, we live in a global economy, and that grain goes in different places, not only to feed humans but also animals. In our case, our Delmarva doesn't have enough land base to supply grain to the 600 million broilers that we have. Right? So someone needs to get grain from somewhere. In this example, that grain comes from Midwest. But remember, it's not only grain, it has phosphorus in it. So when animals, in this case broilers, utilize that grain for their protein, the manure stays local. So that's the part of the story, that if you can send all the manure back into Midwest, they don't have to use fertilizers, and we solve the phosphorus problem here, right? And then the issue is transport. How do you transport tons and tons of manure back into where it should be utilized? So we fragmented the cycle because we have a lot more people in one area, and we can grow things in different places. So it's a good story of human evolution, that how we can be 9 billion people on an earth, which at some point, if you ask people in 1900, they were like, that's unsustainable. But now we can grow, and now we are moving forward with greenhouses and commercial production idea that you don't even have to leave your house. You can get your food in your proximity, and that's partly possible because of the fertilizers. So it's a pretty cool story on how fertilizers have allowed us to be stationary and get our food not from one source but from different sources at the same point. So pretty cool. We don't have to travel to Mexico to eat bananas, right? So that's cool. All right, so many of our soils have high phosphorus, so we just touched on this. That's one of the stories. A lot of manure generated with grain. Manure is being applied to the same fields over a long period of time. This didn't happen overnight. This happened over decades, time frame, and again, over application of fertilizers. And many times there are misconceptions that, hey, we can have a little bit more, because we don't want plants to suffer, and in some cases it's a buffer. So when you're a farmer and you're trying to grow a crop, you want to have an insurance to make sure there are enough nutrients available. So historically that has also happened. Over application of commercial fertilizer has also led to high phosphorus in some fields. And for some recommendation for some of the crops, they continue to be high, and you can guess for various reasons. So here is like soil test correlation. You know, this is oversimplification of a lot of research that has gone into not only Maryland but across the world to figure out how much phosphorus you need in the soil to get the maximum yield that's possible. Right? So we know that if the soil phosphorus level is low, your yield is going to be low. And that's why in our state we have what's called fertility index value for different nutrients. So when you're in the low category, we have this sort of scale, which means that, okay, you know, it's low, which means you're not maximizing the full yield, which means you need to add nutrients. And then you go into the medium, and then you go into the optimum category. So once you get into the optimum category of 100, at that point, the plants don't benefit from excess application. That's why our recommendations kind of cut off at this point for phosphorus and for many other nutrients. So it means there's enough phosphorus available for plants to grow. And the other downside of that is this is where the potential environmental problems exist, because more phosphorus start leaking from that system, right? So in other words, you know, wherever we have soils with high phosphorus level, more phosphorus is going to be lost. So this is our sweet spot. So as you're working on nutrient management plan for other producers, pay really close attention to this number. Because once you get into the high level, now they have to switch to the phosphorus management on those fields. But if you are in that place, this is also not good in terms, it's good not only in terms of, you know, staying away from regulations, but that's also a great way to use manures on the farm fields. So if farmer has access to manures and you keep applying every 3-4 years, you're good, because manure is a great resource that's going to add a bunch of nutrients, and we'll talk more about some of the scenarios yesterday. All right, I think this might be the last one. So again, pH is so critical. So maintain that, apply fertilizers when needed. Again, ban starter fertilizer, especially again, anything that can be done to reduce erosion and runoff, and more importantly, keep the phosphorus levels in that sweet spot of optimum category, which is 51 to 100. This is self-explanatory, you can read it. This is just the summary, so this is your cheat sheet for the test. Let's see, that's all.